part one of the course was basically, well, all the analysis and the mathematics behind convex optimization, right? So convex analysis, the basics there. Most important thing there you need to know are things like convexity of a whole bunch of atoms, and a lot of these composition rules and other rules. These are good to know about, right? Then there was a section on the anatomy of optimization problems, and some of them have names, right? Like you have linear programs and second-order cone programs and geometric programs and things like that, right? In some sense, those names matter less and less. You should know that already, because with things like CVX, a lot of the transformation of a problem that has no name into some problem that has a name, it can be automated, or is at least partially automated. Still, you need to know the name so that, I don't know, you can talk to other people, but that's the idea. And then, of course, there's duality. So, and duality is sort of a big field by itself, and it's really nothing but an organized way to come up with lower bounds for problems, period. That's what it is. In fact, it's quite a trivial way, in some sense, to come up with them. But it's an organized way. And what is shocking is that for convex problems, it's generally speaking, not always, but these are little minor details, with a constraint qualification, it's sharp, right? So that these lower bounds are actually sharp. By the way, we'll see lots of advantage. We'll see lots of uses. You will see, by the way, if you take other courses, you'll see examples where people use duality all the time. They won't even say it, right? I mean, you take a wireless course, and you're trying to figure out how to do, assign powers to channels or whatever, and they'll call it something else like water filling or something. But now that you know the secret, you'll just look at it and say, oh, that's called duality, right? Or you take an information theory course, they're telling you about how to allocate bits to something, and you'll look at it and you go, that's duality. So, okay. Duality also has a lot of aesthetics in duality, where it's useful to recognize that problems that can at first look very different are actually intimately related, right? So, and this will come up when we look at applications a lot. So, for example, it'll be weird things like, again, if you're in statistics, or if you have taken some advanced machine learning courses, you would know things like this, but you get weird things where, duality of you get maximum likelihood estimation problems. The duals are things that look like maximum entropy or Kullback-Leibler divergence type things, right? And so, by the way, if you don't know what I'm talking about, that's fine. I'm being very obscure now, but I want to just point out that this is going to permeate lots of things you've seen. And actually, in various areas, it's completely well known. I mean, people know these things. Okay, so now we're going to start another section of the course. It's the middle section, and honestly, this is the payoff. So, I mean, the truth is you've already seen enough. You're already being paid right now. I mean, the homework is now fun, it's useful, and so on. Well, that's my opinion. You're the one doing it, but I still say it's fun and it's useful and stuff like that. This is really the payoff of the course, right? That what we're going to do is for the next couple of weeks, we're just going to look at various application areas, one by one. And we'll look at some topics. Some will be obvious. Our first topic here is going to be totally obvious. Actually, some will be less obvious. I mean, we'll look at some weird geometrical ones and some ones in statistics and stuff like that, and they won't be totally obvious. Actually, watch out, because some of the most useful material is in the totally obvious stuff, like the stuff we're about to do, is shockingly elementary and unbelievably useful. So this is it. This is also, by the way, the material that's not in any traditional course on this material, right? Because the traditional course segues immediately from convex analysis to basically deadly boring, long, complicated proofs of complexity of algorithms, right? So this is the part that's missing. So, okay. So we're going to start in. By the way, these problems have been categorized into gross areas. This is approximation and fitting. But we're going to see that this will overlap, of course, with things like statistics. I mean, duh. A lot of statistics is basically fitting models, which is in some sense approximating data. So we'll see connections between these things, right? You shouldn't be surprised. Also, I should add that in the lectures here, we're just going to cover some of the high-level stuff. There's a lot more material in the book, and you should absolutely read it. And well, let me put it another way. We will hold you absolutely responsible for everything in the book. So we'll exercise a reasonable fraction of it through the homework, not all, because it's just too much. But we will work with our working assumption is that you will have read all of it. So, okay. So we'll start with just this very general idea of approximation and fitting. And we'll start with norm approximation, and then something which is a vague dual of it is least norm problems. And then something that combines kind of both, regularized approximation, and then we'll look at robust approximation. And this is sort of, this is relatively new. This is stuff from last couple of years or last decade or something like that. So, okay. So norm approximation. Well, I mean, the simplest case is just this. You minimize the norm of ax minus b, right? And you have your data is a matrix A, usually with m bigger than n, so it's taller than, it's a tall matrix, a skinny matrix. And the norm, this is just any old norm on Rm, right? So when you instantiate or specify the norm, it becomes a specific problem, right? It becomes regression or some least squares, that kind of thing. Okay, and now when we're doing this, if x star is the minimum of this, and I should warn you right now, the minimum does not have to be unique. You know that, of course. For the 2 norm, if A is full rank, it's unique, right? But in fact, for other norms, it's absolutely false. So if you do 1 norm minimization, infinity norm minimization, it's incredibly common that there are multiple optimizers. So here, this notation, I don't mean to suggest that there's a unique one, because there need not be. Okay. So what's an interpretation? Well, there's lots of interpretations. The first one is geometric. Basically, what it says is vectors of the form AX, where X varies, sweeps out the range of A, right? So that's a subspace. And then it says you have a fixed vector B. And so the question, and then you have the distance as measured by the norm between B and AX. And so basically what you're saying is, please, this basically says the optimal value of this thing is literally the distance of B to the range of A. So solving this problem is the same as saying, find me the distance under the norm here of B to the range of A. So that's what you're doing. So that's what it is. And you say find a point closest to this, right? And here, I didn't put V, so it's not technically wrong. If I had put any article in here, it would have been A, and then it would have been correct, right? So, okay. Now another way this comes up is in estimation. So in estimation, it goes like this. It says, I want to estimate some parameters x, okay? And what I have is I have linear measurements of x, that's y equals ax, but they're corrupted with noise. And so I add v, right? And so now if I ask you to guess x, interestingly, implicitly, you are guessing v. That's really what you're doing. Because when you guess x, then y minus ax is v, right? And so the problem of guessing x is the same as guessing v. And we'll see that this is exactly the statistical interpretation as well, right? So you're basically guessing that. And so what we're doing is something like this. We're intuitively here, we'll do it quite differently when we do statistics, but here we're saying intuitively that among possible v's, smaller is more plausible. Smaller v in norm is more plausible than larger v, right? So that's the implicit assumption here. And in that case, you would say that solving this problem would give you something like the most plausible value of x, right? Because it's the one where when you are implicitly guessing v, it is smallest as measured by the norm, right? So that tells you about plausibility. It's the least implausible or something. Okay. Another one is optimal design. So here, x is a set of design parameters that you can fiddle with. These could be a force profile for a vehicle. It could be all sorts of things, right? Then you have a linear process. So x causes the results ax, and you have a target, which is b, that you want to hit. If you can hit it, fantastic. But if you can't, you have to compromise and simply get close. And then how do you determine what your happiness level is, or really we should say your irritation level, right? So how irritated will you be if you want b, little b, and get ax? And we'll measure that by a norm. So the norm encodes your irritation level. And then it says the best design is obtained by solving this problem here, because it gets you closest to what you want measured by your irritation. And we're measuring irritation by a norm. Everybody got this? So these are, I mean, don't overinterpret what I'm saying, because what I'm saying is completely trivial. So if you think for a second, oh, I better go think about this or something, you're overinterpreting it. I'm saying nothing deep, and that's going to continue, by the way, for a few more things I'm going to say about this. So it really is this simple. Okay. Okay. Now, let's instantiate some specific examples. If you take the 2 norm, you get least squares, right? And what's an analytical solution of it? I mean, if A is full rank, it's just the least squares. So it's A transpose A inverse A transpose B, right? So that's your least squares solution. Oh, and in that case, I should say that the problem has lots of names. It's called regression in statistics. Least squares, I guess it's called least squares fitting everywhere else. Okay, so that's the so there's probably some other names in specific fields for this, but I can't remember what they are right now. Okay. But interestingly, we can do other things. If you take an infinity norm, then it's actually got lots of names, actually. If you minimize the norm of ax minus b infinity, it's called Chebyshev approximation is one name. Another name is minimax fitting, right? And it's actually quite interesting what minimax fitting is. And it has its uses, right? It basically says I want to fit a model, but what I care about is the absolute maximum error, not the sum of the squares. I care about the absolute maximum, right? And that would be minimax fitting. It's got lots of applications. Interestingly, least squares, of course, is used by zillions of applications, right? It's the basis, it's the workhorse of, giant fields. It's pretty much it's the workhorse in statistics, right? I mean, pretty much, right? All the advanced stuff people do, that's coming online a bit, but bottom line is most people are doing regressions, right? And if you're snickering, making fun of how unsophisticated people are in statistics, don't, because, for example, control is the same way. All of control. Look, there are some advanced control methods. That's fine. Are they working? Yes, they're working. But the bottom line is that most control is variations on least squares. Signal processing, image processing, again, don't make fun of them. It's mostly least squares. Are there more advanced methods coming online? Absolutely, right? But mostly it's done by least squares. So, interestingly, what you find is this is discussed almost not at all in any standard curriculum. Bottom line is that the modern viewpoint, in my opinion, is that turns out, we're going to find out later computationally, this is no harder than that. Shocking, isn't it? It's absolutely no harder, right? But no one knows it, because everyone in this room has been exposed to this, probably in multiple contexts, right? In some class on Fourier series, on some class on linear algebra, probably in other classes. You've seen this, and probably no one has seen this, I'm guessing, right? So, okay. So anyway, back to the main thread here. That this, of course, you can solve this problem as a linear program. Now, that may or may not be relevant, because many times an automatic system will do this for you, right? But nevertheless, it can be written as an LP. What there is not a formula like that, and that's why we don't teach it in some of the more traditional courses, right? So, okay. Here's another very interesting one. It also has a very long history. It's the sum of absolute residuals approximation. Use norm 1. That says minimize this. That's extremely interesting. Again, no formula. You can solve it as an LP. We'll find out later. The computational effort of solving this and this is basically the same. It's the same. There's no difference, right? There's an aesthetic difference if you're locked in a 19th century aesthetic. There's a big aesthetic difference, but computationally, none. This is really interesting, this one. It's an example of what we're going to see later is a robust estimator. The properties are shocking, and it's actually things like that form the basis of actually a lot of modern statistics and machine learning and a lot of other things. So we'll see that. So it's quite different, and these are not new. Well, the fact that this is Chebyshev, and I'm not sure. I'm sure there's a Russian name we can attach to this, and it would be traced to the 30s and 40s. In fact, at Moscow State University, I'll check with my friends and find out what the correct name is, but there is surely one. And so these are not new things. They've just kind of languished in obscurity until the last decade. Now they're the height of fashion, of course, in depending, in different various fields. Okay. So now we're going to look at sort of a generalization of norm minimization. What we'll do is this. We're going to, just to make the notation easier, we're going to introduce ax minus b, and we're going to call that the residual, assign a name to it, r. Okay? And then what you want to do is, essentially, you want all the entries of r small. In fact, if you get all the entries of r 0, that'd be ideal, right? Because you'd have, I don't know, it'd mean you got exactly what you wanted, ax equals b, right? So, but assuming that's not the case, you're going to have to compromise, and you can't have all the residuals 0, right? So what we'll do is we'll penalize values of r by function phi. That's just a function from r to r, okay? That's it. And so we're going to minimize the sum of the penalties. You could divide by m and get the average penalty. I mean, it wouldn't change the problem, but give you a better interpretation or something. Okay? So now you can choose phi. And please don't overinterpret what I'm going to say, because you're going to want to, but what I'm going to say, it actually really is as trivial as I'm saying. So here it is. You use phi to shape how irritated you are with a residual of a certain size. That's it. Okay? So for example, if you take phi is the square function, then that tells you something like this. If a residual is, well, I'll ask you, if phi is the square function, this is least squares. And that implicitly says that if a residual is small, how irritated are you? Yeah, very little. Everyone got that? So the very means it's small squared. Okay. Now, in least squares, if a residual is big, how much does it irritate you? Very much. Thank you. Very much. And the very is not casual, right? It's not, okay, right. So, all right. So, I mean, and that's kind of the idea behind least squares, right? That if a residual is small, you're like, fine. If it's big, not cool, right? So, all right. So, and just don't overinterpret this, right? Well, by the way, we'll have multiple other interpretations when we do statistics about densities and all sorts of crazy stuff and maximum likelihood. But for now, take everything sophisticated out of your mind, and we're just doing this way. Now, if I take phi as the absolute value, I get L1. Let's talk about that. If I take an L1, an absolute value penalty, then if a residual is small, how much does it irritate you? Let's compare how, if you compare that to the square, how much does it irritate you? More, much more, right? So in least squares, a small residual irritates you very little. I'm going to try to say it correctly. But an L1 norm, right, in the absolute value, it says you're irritated a little bit, but relatively speaking, that's a lot. I mean, compared to squares, right? Okay. How about this? With absolute value, if you've got a big residual, how irritating is that in least squares? Very. And in absolute value? It's irritating without the very. Everybody got this? Okay. So I mean, look, I know this sound. It really is this dumb. It really is. Trust me. But this is unbelievably useful, right? Because I think what has not been recognized until relatively recently, and is not by any means fully recognized now, is the following fact: that least squares is the one case where you get some silly 19th century formula, right? But all the other things we're talking about, you can solve just as easily, right? And so people haven't looked at them. So, all right. So let's look at some things. Well, we just talked about the quadratic in detail. Here, let's do something else. Here's dead zone linear. That's this function right here. Look at this. It's linear, and then it's got what people call a dead zone in the middle. So between plus and minus 0.25. You should articulate, what does that mean about how you care about residuals? Well, in this case, it's very specific. If it's less than some threshold, it doesn't irritate you at all. And in particular, that goes two ways. It means that a residual of 0.001 is absolutely no better than a residual of 0.25 here. None, right? By the way, there's plenty of applications of this, and it doesn't, you can think they're going to come to you like pretty quickly. You make, if you have like an analog digital converter and you make a measurement, then being off by something less than your LSB, your least significant bit, it's not better. I mean, you're not better. It's just all you know is that this signal value is in some interval. You don't know anything else. Okay. And the fact that it's linear out once you go outside the dead zone, let's talk about how much you care about large residuals. So you'd say, look, I don't, who likes large residuals? No one. I don't like large residuals. But you don't go nuts about it as with a quadratic. That would be the explanation. Everybody got this? Now, by the way, we're anthropomorphizing all this, but what we're going to find out is this does exactly what you want, right? So, okay. So here's another weird one. Here's log barrier with a limit a. So there's just an expression here. It doesn't matter what it is. Well, I can tell you what it is. It matches the quadratic almost perfectly over plus minus, over a pretty big range. It matches the quadratic very closely. But then what happens is it accelerates and goes up to plus infinity. Someone explain that to me. It means I do not even want to discuss the possibility of residual more than plus or minus 1. I won't allow it, right? But for smaller residuals, it's just like least squares. Okay? So these are the idea. Now, the whole point of this is that then you would craft your own penalty function. And let's just try one. Suppose I'm doing least squares fitting or regression. So I just want to minimize, I want AX to equal B. But suppose I said that I care about, and take the residual R, and then overfit, let's say that being above is okay. I don't want to be below. I care 4 times as much about being below. So you could interview me and you could say, tell me about the residuals and the model and the data that you want to fit. And I'd say, well, I want it to fit. And then someone would ask, well, how do you care about big residuals? And you'd say, I don't like them. Of course I don't like them. You say, but I mean, will you go way out of your way to not have big residuals? And you go, no, if we have to have some big ones, we'll have some big ones. Okay? Everybody, we just nailed, by the way, the asymptotics of the penalty function. And then you'd say, well, tell me about under and overfitting. Is it symmetric? You know what under and overfitting is. It means you look at an entry of B and you look at an entry of AX and you compare the numbers, right? If you say, I don't care, I mean above, below, it doesn't matter to me. But suppose you said, no, actually there's an asymmetry there. It's much worse to underestimate. So if AX is less than B, that's bad, right? How bad? You go, well, a reasonable factor or something. It's 5 times worse. By the way, there's a bigger picture here, which actually fits with all of optimization, that the idea is not to focus on the algorithm that produces X. What you do is your tools is the problem. You formulate phi, and the optimization will carry out your wishes to the extent that it can, right? So that's the idea. So you should express your wishes in fitting by setting a penalty function or something like that. Then let optimization sort out the details. Everybody see what I'm saying? I mean, these are totally obvious things, but believe me, they have not been internalized by the vast majority of people doing kind of mathematically sophisticated things. So let's look at here's an example, very simple. We just generate a random data problem with 100 measurements, 30 parameters that we want to estimate. These are, and then we just solve various problems. We'll do one, we'll do a L1 norm, we'll do least squares or regression, we'll do a dead zone linear, and we'll do this analytic center, or what did I call it? I forgot what I just called it. Log barrier, okay? Yeah, log barrier. So we'll do log barrier. Yeah, by the way, the name of the point is the analytic center. We'll get to that later. But okay, so, and what's plotted here, let me explain what's plotted. This function here, so each of these, that's 1 norm, 2 norm, well, square, right? Dead zone linear, log barrier. And you see the actual function plotted on some scale here. So this function tells you kind of your irritation at having a residual of that level, okay? And then what's shown in here is the histogram of residuals that you get. right? So you get different x's in each case, right? And you get different histograms. We'll start with least squares because this would be this is kind of the starting point for everything. Here they are. Well, it's kind of nice. You get get a bunch that are out here. You have a few that are big, not so big, and but they're all bunched in here. Okay. Let's look at the L1 case. You get something bizarre, and it is completely explained intuitively by what we talked about. The first thing you see that catches your eye is that's a different scale. Is you got this giant pile of x's that of residuals that are flat 0. And by the way, it's not that they're small; they are actually 0. Okay, so so I'll give a very simple intuitive explanation for this. The incentive to drive a residual to 0 holds up until it's 0. So if a residual is at this value, there's still a strong incentive to reduce it. Okay? Now, that's completely false for quadratic because the smaller a residual becomes, the less incentive there is. An incentive is just the slope of this thing. It says, how much benefit would I get in reducing the objective to make that residual slightly smaller? And the answer in least squares is you have a diminishing residual benefit, right? Here, it holds up to the very end. Okay? And the result is a whole bunch of them become 0. By the way, for those of you who've taken a machine learning class, a statistics class, a whole bunch of classes, you will recognize this, that you should already have heard about things like L1 and sparsity and things like that. And you're going to have in your head burned a connection between L1 and sparsity, where things are actually 0. And in fact, it turns out it's not L1, it's just the point. It turns out the point is here. So the one we looked at before, our asymmetric one, would have the same property. All right. But the other interesting thing is look at that. There's a residual out here which is like 1.8. And you didn't get that in the L2 one, right? Because 1.8 is a big residual, and in least squares, you care about that a lot, 1.8 squared, right? And so, again, I'm anthropomorphizing, but in least squares, pushing these down here was a good trade-off in terms of these things split and moved all around here and so on, that sort of stuff. I mean, this is all just anthropomorphization of all this, but this is the idea, okay? Here's dead zone linear. And you see something very, very interesting, that if your residual is between plus and minus a half, we don't care at all. 1/2, a residual of 1/2 is, in terms of irritation, no better, no worse than 0. That dead zone linear says there's an incentive to reduce a residual. The incentive entirely disappears once a residual is hit 1/2, right? And in fact, that's what's happened, right? So these are sort of residuals that, well, why not? But they weren't forced to be between there, right? They just happen this way. And here is the log barrier, and sure enough, as required, they've all been crushed down here. So now let me introduce some really cool stuff. You can make cool Frankenstein-like. We can cut up penalties and re-sew them together and make things that I guess don't come up obviously. Here's a very famous one, is the Huber penalty function. The Huber penalty function is this. It's quadratic up to a threshold, whereupon it transitions to linear. And so this is the Huber function here with threshold m. Actually, it's a very important function, and for, I would say, 80% of where people use least squares right now, my guess is that in 80% of those cases, the application would be improved. The performance in whatever the application would be improved if it was replaced with a Huber, and no one knows that, right? So, I mean, people know that. People do advanced statistics. They always do this kind of stuff, right? But in lots and lots of other areas, they don't know that. So that's a Huber function. And first, let's just talk through what it means. So the Huber function says something like this. If you are below the threshold, if a residual is below the threshold, it's identical to least squares. It basically says it's least squares. But if you go over the threshold, it's radically different from least squares. And what can you say about a Huber penalty as opposed to least squares? It looks like an L1. And it is a penalty that it's more relaxed. So you would say something, you could just guess this. You would say that if you do Huber approximation, let's say, you'll end up with something like this. Compared to least squares, it's going to be, if all the residuals are in the threshold, below the threshold, it's exactly the same as least squares. But what it'll do is it's going to be much more relaxed about having a couple of outliers. So it will actually allow a couple of outliers. It's not going to like it, but it's not going to go insane like least squares will, and it won't actually ruin everything else. It won't increase all sorts of other things to try to improve one. Okay, so it turns out this is a robust estimator. We'll see lots of this in the future, but it's a robust estimator. It works unbelievably well, and so let me show you the kind of thing it works on. So here's a picture with 42 points. Okay, so 40 points are obviously scattered on that on the line, and these are two obvious outliers. Okay, so we just made the data. This is just plotted so you can see it. Obviously for fitting data in 2 dimensions, you don't need any fancy convention. You use your eyeball to do it. So that's not what this is for. Okay, but this is just to illustrate what happens. Okay, so there's your data. If you do the least squares fit, you get this dashed line here. Everybody see that? And the discussion is extremely simple. It's basically, look, that is so big that when you square it, it's gigantic. It's extremely irritating. And least squares will actually bend the fit to reduce that big number which you're squaring. And it will take a hit on all those other numbers. Everybody got that? Okay. Now, and by the way, in your head, you can take these two things and you can move them this way. You can make them much worse. I can make the least squares thing actually flip over and have the wrong slope. Okay? Now, by the way, if you think, of course, in our plotting a silly data with one variable, it's goofy, right? But the point is, you get the same thing when you are fitting things like things in dimension, in very high dimensions, like dimension 100. At which point, by the way, your eyeball is no good, just for the record, right? So the Huber fit is the dark line here, right? And it's false to say that it's unaffected. That is actually false, because I could also show you a fit where I removed these two, right? And that black line would move very slightly. Okay? So and would then fit those things perfectly. By the way, that's also a standard 2-step procedure in outlier. You first use something like a Huber or robust estimator to guess which are the outliers, remove them, and refit. So there's a whole lot of stuff on this. So this is this. By the way, this thing works so well for a lot of sort of practical data. People blabber on and on about things like big data and stuff like that. So things like these robust estimators are absolutely critical in a situation like that, right? Because when you have a billion pieces of data and 1,000 of them are complete and utter nonsense, they're just outliers, that can render least squares utterly useless. And these things will just power through it in shocking ways, where you can take a problem. We'll have some homework problems on this, but it'll be shocking. You take something, you add in outliers at the 10% of the data will be outliers, 20, 30. That's usually a threshold point where it fails. But you can get just absolutely, a lot of times you have to double check that what you're looking at is the right thing. You think maybe you've used the true parameter, not the estimated one. These things work so well. So, and this is something that, it's implicit in a lot of modern statistics. It's implicit in a lot of machine learning and things like that. So it's a very good thing in my opinion, everyone should know about this, these kinds of things. So we'll look now at something, it's like the dual of the approximation problems or norm approximation problems. And that's a least norm problem. And the basic idea is this. Here you have equality constraints. So in this case, A is not generically tall. It's generically wide. So A is a wide matrix. And this says that I have something like M equality constraints on X. Presumably not enough to completely constrain X. Then it's a silly problem. It has one feasible point. And then among the x's that satisfy ax equals b, we're going to choose the one that has minimum norm. And you've probably seen this in some class. If you took 263, this was a least norm problem. It was the 2 norm there. So what's the interpretation of this? And of course, I should say something here when I say equals argmin. If this norm is strictly convex, and that would be the case, for example, for a 2 norm, then it's unique, of course. But it can easily be not unique, right? So we should say something like, well, one notation would be x star is in argmin, because one notational convention is that argmin returns the set of minimizers. So by x star equals argmin, we just mean it's a minimizer. So the geometric interpretation is this. We have an affine set that's generically given by the set of x such that ax equals b. So we have this affine set, and what we want to do is find the point closest to 0 in that set, right? And a simple, completely elementary variation on this is where we project a point in a non-zero point onto that set. So that's the idea. It's a projection of 0 onto the affine set. Estimation is this. The idea in the estimation interpretation is something like this. We interpret b equals ax to mean that we have m perfect linear measurements. So there's no noise, nothing. They're perfect. And then, but we have n parameters to estimate, and we have more parameters than we have measurements, right? So I have 150 parameters to estimate. I have 50 measurements or 100 measurements, something like that. And that leaves me basically 50 unknown dimensions or something like that. So ax equals b, in that case, we interpret as the set of parameter values that are consistent with the perfect measurements, right? So this, if you were to put a comment here, you would say something like consistent with measurements, like this, right? And the assumption is the measurements are perfect, right? So that would be that. And then the interpretation of minimizing the norm is you then choose most plausible, right? Choose the most plausible point, right? And here implicit is the following idea, that the larger x is, the less plausible it is, right? So that's the idea. In other words, you're in some situation where there are many parameter values consistent with the measurements. So anybody who chooses a x with ax equals b cannot say to another person who chooses another x that satisfies ax equals b that they're wrong. What one can do then is just talk about which is more plausible or something like that. And so the idea is that the norm is here used as a surrogate for, I should say, implausibility, because the larger the norm, the less plausible it is. And by the way, we'll connect this, possibly even later today, we'll connect this to a statistical interpretation. Another one is design. So here, you think of x as a bunch of design variables. These are inputs. For example, this could be forces that you apply to a vehicle or something like that, right? It could be voltages or current drives that you're going to send to a motor, or current drives that you're going to send to an antenna, right? Something like that. Then ax gives you something like the result, right? So this gives you the result. So, and it might be something like this, that you choose 150 forces to apply, maybe at different times, different actuators. But actually all you care about are maybe 6 or 8 things at the end. For example, the position and momentum at some final target time, something like that, right? In which case, ax gives you the result of the action x. Then b is actually your desired action. And so any x that satisfies ax equals b is valid. It says basically, find me a set of forces that will take my spacecraft, move it over to here 12 seconds later, and arrive here, with this position and momentum, right? So that would be, lots of x's do that. And here what you're doing is you're saying, please find me an efficient one that minimizes a norm. Could be 2 norm, could be 1 norm. 1 norm would be closer to fuel usage in a lot of cases, something like that. It could be infinity norm. It could be anything, in fact. Okay, so these just interpretations of the problem of minimizing the norm of x subject to ax equals b, equality constraints. Right. Oh, I should say that one nice thing about our approach to these, which is simply to look at that and simply say, that's a convex problem, period, right? One nice thing is, you can mix and match. If all of a sudden somebody comes back and says, oh dear, I need to add some constraints here, like for example, the x's have to be between plus and minus 1. It's not a big deal for us. We just add this constraints, right? So, okay. I'm not showing them here just for simplicity. Okay, let's look at some specific examples of least norm problems. Here's one. The most famous one is you take the 2 norm, and in fact, what you really minimize is not the norm, but the 2 norm squared. Not the 2 norm, but the 2 norm squared. And this is the same because minimizing 2 norm squared and 2 norm is the same. It has the same solution. And the optimality conditions, you work them out. The KKT conditions are linear. They're a set of linear equations, so you can solve them exactly, and there's a formula for it if A is full rank and all that kind of stuff. And you've seen that in 263 or some other linear algebra course, right? So, and that's why this is of course extremely widely used, right? Because it fits everything, right? It looks like it's simple, fits the 19th century, formula model and all that kind of stuff. Okay. Now you can use other things, which is actually quite interesting. You can do things like this. You can actually take the L1 norm, and this is a very interesting problem. This says minimize the norm of x1 subject to ax equals b. Okay, and this is something actually that's quite in vogue right now and has been maybe for 5, maybe 10 years now. It has no analytical solution in general. Well, I mean, except for very silly cases, has no analytical solution. So it's got various names. This one's basis pursuit. And let me ask you, in view of the discussion we had last time, now last time we talked about a penalty function and how the shape of the penalty function has an influence on the distribution of residuals. That discussion transposes perfectly to this situation, right? So here, the idea is that if you have a penalty function, here the penalty is embarrassingly simple, it's the absolute value. But what it does is that's going to shape the distribution of x's. And what I would like to know from you is, what do you imagine the solutions of the basis pursuit problem look like? What you would expect, and turns out in fact to be true, is that when you solve this problem, most of the x's are 0. Okay? And I mean, there's various ways. You will observe this as an empirical observation, and in fact, you can prove various things about that, and so on and so forth. So in fact, this is a heuristic for getting a sparse solution of ax equals b, right? So, okay, and this is going to be a theme. It's going to kind of follow us through the rest of the course, and so on. So, okay, and we'll see a lot about this. Okay, so, well, we've already been talking about this, but the least penalty problem says that you choose a penalty function phi here, and then you minimize the sum of the penalties subject to a equals b, and then you would choose phi to shape to get an x that you like, right? And by the way, there's something quite interesting about it because it has something to do with how people don't talk about it a lot, but there's the question of sort of the entire design flow. How do you use like convex optimization, this kind of thing? And in fact, there's this big trend across many fields to move away from something that's a direct solution that says, oh, I want a sparse solution, so here's what you should do with the data, towards one where you put one level of indirection in between. And what you do is you form an optimization problem. And what the user does is mess with the optimization problem. And then you let some numerical method work out the actual solution, right? So, I mean, this is a big trend across many, many fields, right? That, for example, in areas like control, signal processing, even statistics, you move away from this idea of here's what you do to the data, and instead, what the designer of a method is really doing is actually designing an optimization problem. You change parameters here and there. Something's too smooth, or if something's not smooth enough, you add a little regularization and you crank that up. But you as the user are not actually figuring out exactly how to transform your data into your estimate or something. Everybody see what I'm saying? So this is a it's a big picture observation, but it's happening. It's prevalent. Okay. Well, the parent of these two problems, least norm and then norm approximation, is just regularized approximation. In fact, there's even a more general parent. And the basic idea, so regularization it's kind of ubiquitous across lots of fields. And it's basic, the correct way, I think, to think of it is it's a bi-criterion problem. And it basically says I care about two norms, each of which I would like small, right? So the norms are, this is the most traditional setting. The first one is something like ax minus b. That can have lots of interpretations depending on if you're doing a statistical model or data fitting. This is your misfit. X is your model. Ax minus b norm is a measure of how well your model agrees with the data you have observed. That's something like misfit or fit. Um, Norm X is basically how big are your model parameters. And we'll talk in a minute about why would it be that you would want small parameters. Actually, there's some very good reasons why you would want small parameters. Well, like many good ideas, it can be justified from like 5 different, completely different points of view. So let's look at some of them. So the idea here essentially is you're saying, you know what I want is I want a good fit. I want AX to be about B. But I want to do it efficiently. I want X to be small. So this is the essential idea, right? Oh, and again, these ideas are all very simple. So if you're not following, don't overinterpret what I'm saying. What I'm saying is so simple that there are no subtleties here, none, right? So, okay. So when would this come up? Well, in estimation, it might be something like this. You'd say, well, I happen to know. I mean, what I'm observing is y equals ax. So ax minus y or ax minus v or something like ax minus b, if b is what I measured, is v. And so this is something like the norm of that this thing, and you know that that's small. But I have prior knowledge that x is small, right? So, and that's what this term does for me, right? So that's what that says. You could have optimal design. You could say, actually, I don't insist that ax equals b. I will give up on ax equals b. I will simply get close enough. Close enough? Well, this is a bicriterion problem. So you have a whole Pareto-optimal curve, and you would determine where to operate on that curve once you see the curve. Then you'll look at it and say, okay, fine. I don't need to. I mean, if I'm within 3 millimeters, that's actually fine. Especially if that allows me to use, 1/4 of the fuel I might have used otherwise, right? Something like that. Okay, so there, the idea is you're willing. You don't even, you're willing to not have ax equals b. You'll give up a little bit on that, and hopefully you'll take as a benefit for not doing that exactly a small x, right? So that's the idea. Another interpretation is robust approximation. And this is something we're going to talk about later. This is quite a modern interpretation, and it's extremely important. And the idea is something like this. You really just want to fit a model. So you really want norm ax minus b to be small. That's really what you want. Problem is, you don't quite know a, right? This is extremely typical, right? That the a's are measured or something like that. You don't quite know what they are. And by the way, this can happen in a design setting. It can happen in an estimation setting, right? In a design setting, you say, you know what? I do know. I know the moment of inertia. I know the moment of inertia. I know the mass of the vehicle, the CG. I know all these things pretty well, but actually only about 1%. No better than that. And what that says is, if I apply a bunch of control surface deviations to an aircraft, and I ask where will it be in 22 seconds, the answer is actually, technically, you don't know, right? Because, I don't know, there's plenty of air. I mean, hopefully you have a pretty good idea of where it's going to be, right? Because otherwise you're in deep trouble. But the point is that there's really like a cloud of where it might be, depending on what you do. Everybody see what I'm saying? It should be a tight cloud, one hopes, right? But the fact of the matter is, you don't know exactly what's going to happen, right? So that's the idea. Okay. So then you say, well, what's interesting about this is how much is your x affected by changes in a, and that we can even work out. I mean, this is going to be an intuitive one. We'll look at this more carefully later. But so what you do is you think of a as being sort of the nominal one, and delta is a matrix, presumably small, which is basically your error in a, right? So this is what you have, right? So for an aircraft, this is the nominal model that assumes that your estimate of the mass, moment of inertia, blah blah blah, all these things are perfect, right? They're double precision perfect, right? This is basically these are variations due to the fact that, these things are manufactured, things vary by 1%, all sorts of things happen, right? That's what the delta is here. And if you look at this equation, we're going to work this out, but it's very, very simple. What you get is ax minus b, and then plus delta x. And what you see very clearly is the following, is that the errors in A multiply x. And so, for example, suppose I chose x to be 0. How much would that be affected by model errors, by the delta? Not at all. Right. And you can see immediately, I mean, this is very intuitive, but the basic idea is, oh, by the way, these are sometimes called multiplicative errors. That's a name you will hear. And it makes perfect sense because it's an error in A, which then multiplies your choice x. So it's a multiplicative error. And for a multiplicative error, it is in your, if you want to be less sensitive to a multiplicative error, then here's what you want. You want x to be small, the thing. Everybody see this? And so this is why a small x would be preferable, right? That it would be less sensitive to errors in A. Yeah, that was a long description. It's not supposed to be fancier than what I just said, but that's the idea. And I can give you yet another interpretation of it. I mean, in some sense, all these interpretations come around to the same thing. Another one is this. You have y equals, you have a model like this, estimation. You have y equals ax plus v. But the truth is, you really have something like this, right? You really have a nonlinear model. However, near where you're looking right now, y equals ax plus v works. That's provided x is small. Okay? So the idea there is this sort of tells you your nominal error based on your, say, linearized model. This says, please have x small, because the smaller x is, the more accurate, the more I trust my linearized model, right? And in fact, in that case, the term that constrains x either via regularization or as an additive term in regularization or as a constraint, if it's a constraint, it's called a trust region constraint, which is a beautiful term because it basically says, please estimate x. I want norm x minus b small, but I want norm x small. And someone says, why do you want norm x small? Do you care? And you go, actually, no, I don't care at all how big the parameter is. The problem is I have to add that there because if x gets bigger, my model ax is no longer accurate. Everybody getting this? Yeah, get the idea. It's pretty straightforward. Okay, all right. Let's look at some simple cases. So how do you solve a bicriterion problem? You scalarize, right? This is the simplest method. And so you take the norm of ax minus b plus gamma norm x. For us, that's a convex problem. No big deal. We solve it. Okay, so that's fine. And gamma is a positive parameter. You sweep it from 0 to infinity, and at the two extremes, you could get the extreme points by solving a constraint problem or something like that. Okay, and so this traces out the trade-off curve. A very traditional method is to square the two. You get the same trade-off curve, and by the way, that's something you would want to check, right? That in fact the curve of solutions here, parameterized by delta, is identical to the curve of solutions parameterized by gamma here, right? So in fact, you could even work out how delta and gamma are related, right? And it's not totally straightforward, and it has to do with the particular problem. But these are two parameterizations. Okay, so if these are two norms, and the reason generally one squares a norm, I mean, there's several reasons, but the most traditional one is when you square a two norm, you get a quadratic function, which is nice and smooth, and the derivative is linear, and and then all your you have a formula for the answer, right? Okay, so most famous there is Tikhonov regularization. Oh, and I should say in statistics it's called ridge regression. Is the name in statistics. There's maybe another one, but it's called ridge regression. And this just turns into a single least squares. I mean, you can solve this analytically. Of course, it's two norms, right? And the solution, you can either stack it and make a big least squares problem, or you just get sort of an analytical solution like that. Okay? And that's the thing. Now, the horrible reason to use this, the one that I don't like at all, and is in fact probably the most common use of regularization, is someone says, what are you doing? You say, I'm adding regularization. Why? And you'd say, because without it, I was getting numerical. My solver was sending complaints to me. Right? So Everybody see that? That if you add delta here, this is just now works. It has to work perfectly. You can never get a complaint that says, inverse condition number big or, numerical, something like that. It's not going to happen. Can't get something singular working precision. So let's look at an example, and this example actually it's very simple, but it's going to be an example actually of it's meant to illustrate exactly what I talked about earlier, this idea of a design flow, right? How do you use these things, right? And this will be one from control, if you like. This could just as well be statistics. It could just as well be anything else. It could be image processing, video processing. It could be anything, and you can construct a similar story, right? It could be finance, right? So let's look at this. Here's the idea. I have a convolution system. So I have I apply an input, u, scalar input over at various time intervals. It could be a force I apply to something. It doesn't matter what it is, right? And something I call the output is a convolution of the input with some convolution kernel, or in EE dialect, that's called an impulse response. Okay, but that's dialect. Okay, the standard term is convolution kernel. Okay, so and in mixed company, you should always say convolution kernel. So just okay. So the input design problem is choose this input u so that y does something you want. And this is just going to be a very simple example to show what a typical design flow looks like. So here it is. What I want to do is I'm given a desired trajectory and I want to track it. That's it. So and I want to make I have to give a measure for mistracking, and so I'm going to call that JTrack. And if you can't think of anything, if nothing immediately comes to mind, then you should just use the squares, just as through historical, to follow in a historical tradition, and what I mean, it's not a bad thing, right? I mean, by the way, if I were to make this the sum of the absolute values, it would change the result. And you could even kind of guess what would happen when you do that, right? If I were to make this the infinity norm, right, that you would call that something like minimax tracking error. You might give a name like that, and you would get different results as well, right? So, but here we just take the square just to make it simple. Okay. Now at the same time, I want u not so big, right? So I'm going to introduce an objective called the magnitude, Jmag. And these are, by the way, if you look at these, they're quadratic forms, right? So far, right? Because they're square. They're squares. They're sums of squares. And I'll take an input. This tells you how. Well, you shouldn't say smooth. How wiggly the signal is, or something like that. And it's going to be the sum of the difference of the first differences here, right? And now I can ask some questions like, when would JTrack be 0, which is its minimum possible value? It means you have your y is equal to y desired, and yes, and a good name for that is you might say that you interpolate the desired thing, or you might say you achieve perfect tracking, meaning that the output absolutely tracks what it is that you required. Okay, so that would be that. When would the input magnitude objective term be 0? When u equals 0. Okay, so in which case, by the way, your tracking error would simply be some y desired squared, right? Because your output would be 0 at that point. Okay, and how about input variation? When would that be 0? Constant, exactly. So if you were to crank up the coefficient on input variation very high, you would expect to see inputs that were constant, right? And at the same time, they're attempting to track and things like that, okay? And you could go on and on. For example, you could have a second finite difference, which would be something like a smoothness measure, and that would be something like ut plus 1 minus 2 ut plus ut minus 1. That's I don't know if you recognize that, but it's the famous minus 1, 2, 1 in a tridiagonal matrix or something. It's a second difference, right? And that would give you something smooth. And when would that be 0, by the way? Linear, exactly. So if u looks like that or that would be 0, right? So, okay, great. So what we'll do is we'll just make this a regularized least squares problem. We'll take the tracking error plus delta times the derivative error plus eta times the magnitude error. And I mean, this is a least squares problem, right? So I mean, we just solve it, right? This is the idea. We get a least squares problem. And then the idea now is that delta and eta are knobs that you will fiddle with to get something that you like, right? And you could do this in a formal way and actually do 10 values of each. I mean, it's a trivial problem. You could do 10 values of each and then just make a big 10 by 10 matrix and actually plot all these things, look at them, whatever you like. You could have two big knobs in front of you that labeled, delta and eta, or two sliders or whatever on some user interface, and you could fiddle with them and see what you like, right? So that's the idea. Okay, so quick example here. Here are three Pareto optimal solutions, right? So the first one has delta equals 0, and that means we're putting 0 penalty on the variation in U, right? So fine. We're putting a small weight on the size of U. That's eta, small. And here's the input and the output. And two things are plotted in the output. You can't see there's a dashed curve here, which shows you the desired one. The desired one is just this kind of square wave thing. That was dialect. That goes that jumps up and then jumps down, right? Like that. So that's the desired one. And you can see if you look at this that we're tracking quite well. Well, you can see there's little errors right at the transitions and so on. And this is the input that does the trick over here, right? So that's the input. And you can see the input gets as high as, almost 5 positive, and it jerks down to like minus, I don't know, 7.5 or 8 there. Okay, so that's it. And you can also see that the input is quite wiggly, right? So fine, that's just one point on the trade-off curve, right? Then you'd say, well, in the middle, what we're going to do is we're still going to have no derivative error, but we're going to crank up eta. And we expect, so that means we're going to add more penalty to the size. And so what we expect is the size of U to come down. And by the way, we're going to pay for that in tracking error, right? So, and indeed, if you look on the right, you can see here, the tracking error probably is mostly accumulated around these endpoints, and it's pretty small. Here you can see you can actually see some pretty substantial tracking error here. Everybody got this? The difference is, look at this. Instead, we've basically halved the input, right? So with half the input, and so if this is good enough for you, great. I mean, this is kind of the idea, right? And finally, in the last one, what we're going to do is we are going to we're going to now turn on a bunch of smoothing regularization. And again, you pay for it in terms of tracking. Maybe this is good enough for you, maybe not. But you can see immediately what happens. Things like these, which rack up a big bill in the derivative cost function, now are smoothed out, and you get something like this. Okay, so this is not supposed to be. It is not complicated. It is simple, but the idea is this is what you do, and you would typically sit there and turn knobs and see what you like, right? And this could be any application area, right? This could be image processing, where you turn a knob and you go, no, it got too smoothed, and then you crank it down the other way, and now some of the noise comes back, and then you turn another knob, and this is how this goes. So let's look at another area. It's also a very simple bi-criterion problem. It's signal reconstruction. It's quite straightforward. It's this. What I have is I'm given a corrupted signal. That's x, corrupted. Okay? And what I would like to do is to come up with x hat, which is supposed to be an estimate of this it's an estimate of the signal before it was corrupted. Okay? And that's what I'm going to do. And so I want x to be close to x corrupted, but I don't want it to be equal to it because it's been corrupted. And what I'm going to do is I'm going to have a second function here, which is known as, it's got lots of names. It's a regularization function, or sometimes people call it a smoothing regularizer. Okay? And so that's this function phi of x hat. And the idea is, by looking at a trade-off between these, I'm going to do some, this is a principled way to do smoothing or something like that, to smooth a signal. All right. And the model is something like this. You have some unknown signal. You observe a corrupted version, and then you're going to solve this problem. And examples would be something like this. So simple quadratic smoothing would be you simply take the differences squared, like we did in the previous example. The sum of the absolute values, that's called the total variation regularizer, right? So that's completely standard. So that's actually a standard term. Let's look at an example. It's a simple example, right? So here's some signal. It's 4,000, time samples or whatever you like. Here, this is the original signal, and this is the corrupted one. And I mean, this one's kind of goofy because, you've taken the signal, you've added some, and you can see that the difference between the signal and the corruption. You can see that the corruption is very like high frequency or something like that. Again, so it's kind of obvious, right? So here, what you do now is we simply use a quadratic smoother, and what you would get would be things like this. So this is with a little bit of smoothing. This is what you'd reconstruct. This would be substantially more and even more still, right? So that's the idea. And you might say that's a little bit too much, and then that's just about right. Right. Now, unfortunately, for smoothing problems like this, there really aren't any particularly good ways to choose the level of smoothing you do, except maybe aesthetically. I mean, you have to have some side information, right? Or you could have some cases where you actually knew what the exact signal was, right? So that then you could actually do reasonable things like cross-validation. Here's one, and this is much more modern. By the way, total variation reconstruction. This is introduced maybe only in the 1990s, so this is pretty relatively recent. And it's actually quite interesting and quite stunning. In fact, I've tried to get some audio recordings of this. I mean, I haven't tried that hard. I should, because they're amazing. I'd put them on the course website or something like that. Anyway, but I'll explain that in a minute. So here's a picture. What I have is, here's the original signal. Right? It's got a smooth component, but these kind of jumps every so often. I mean, this is all just made up, right? So this is just to illustrate what happens, right? So here you have this signal, and then we add this high frequency noise to it, like that. So that's the corrupted signal, right? Now, one of the problems here is that you don't have this frequency scale separation, right? Because the original signal has these jumps, and a jump, again, if you know about Fourier analysis and all that kind of stuff roughly, is going to contain a lot of high frequency. So you don't have the spectral separation of the underlying signal and the noise here. And the result is, if you do quadratic smoothing, which in fact is a linear operation, it's just a low-pass filter, frankly, is what it is. And what you get is this. If you do some low-pass filtering, well, sure, this gets smoothed out. That gets attenuated. But you can see as you crank it up to smooth out more, you can see exactly what's happening here. That a transition that in fact was a single value has now widened, and now it's taking place over, ooh, that's a lot, 50 or something, right? So a transition that went in like one time sample is now happening over 50, right? So, by the way, if this were audio, this would make something sound very muffled. If this was the attack caused by a drum, right? Someone hits a snare drum, you will get something that looks like that. And if you smooth it like this, and instead of the attack, rising in 10 samples, 48 kilohertz or something like that, instead of 10 samples, it goes at 1,000. It sounds like a thud, and it doesn't sound like a drum anymore. Okay, so all right. But let's do total variation denoising, right? So total variation denoising does this, and actually we can see a lot of things here that you would predict. So the first is this. This is where you have put a lot of total variation denoising in, and you're beginning to see something pretty cool. When you crank up something which is basically the L1 norm of the difference of x hat t plus 1 and x hat t, again, you should start now, and by the end of the course, it should be completely ingrained in second nature. But you want to make connections between things like L1 and sparsity, right? And that's the very simplified model, but it should really be kinks and sparsity, right? So let's look at L1 and sparsity. When someone says, please minimize, well, it's part of it, right? If they say, please minimize this, right? What you would expect is that if the coefficient in front of this is high enough, right, that a whole lot of these numbers will be 0. And that says that if you do total variation denoising, you should expect a piecewise constant signal. Because a piecewise constant signal that's what it means. This is like a derivative, this first difference. And if you have sparse derivative, it means you're piecewise constant. Everybody got that? By the way, if this were the second difference, and I put an L1 norm, and I minimized, what would you expect to see? Piecewise linear, exactly, right? And if I took the third difference, what would you get? Piecewise quadratic. And by the way, those would be splines, just for the record. You'd get splines, okay? So this is sort of the idea. Now here what's happened is, you are tracking this, right? But what's happened is your regularization is so high that things like that just got constant, right? You've lost the fact that this is varying here, right? Oh, I should add also kind of a cool thing. If you do this on images, say grayscale or color stuff, you get very cool stuff. Things start looking cartoonish, right? Because you have a whole bunch of, you have whole regions where it was one color or one shade or there was some gradient. It's just like now replaced flat. So I think you can even imagine what this looks like, right? So, right? This is so if you do total variation regularization on an image, what happens is, as you at first you have 1,000,000 pixels, you're probably going to have 1,000,000 grayscale values, right? I mean, there'd be no reason for any of them to repeat, right? If they do, it's an accident. You turn up total variation regularization on an image, and that'll jump down dramatically. And after a while, you'll have only 1,000. And then you keep turning it, and at some point, you'll have like 10 gray levels, right? And by the way, it'll still be completely recognizable as the image you wanted, right? But anyway, so I'm just saying, these things apply to everything, right? You'll see these all over the place. So here, you can see this is where we might have maybe not quite enough total variation regularization because you can see there's some squigglies there, and this is kind of the proverbial just enough, right? Something like that. Finally, there's a big thing. We'll look at this idea of robust approximation. So here, we've already seen a little bit of this, hints at it, right? So the idea is you want to minimize, let's say, norm AX minus B, but the problem is you don't know A. Now, I should add, this issue is universal actually in all optimization problems, right? That you have data in an optimization problem. And, we can talk a little bit, some generic things to say about data. When values that are 0, 1, -1, sometimes 2, -2, 1/2, things like that, those are probably really those numbers, right? Because it may be some coefficient that makes sense, like you're basically saying, this thing's equal to that. And that would reveal itself as a 1 and a -1. And this really probably are 1 and -1. Any other constant other than the ones I just named and maybe a handful of others, generically speaking, they have a provenance. And you can trace it back. And they trace back to models of things or measurements or experts or econometric models or mechanics or physics models or something like that, right? And in fact, if you trace them all the way back, you'd say, oh, that came from a finite element calculation and blah, blah, blah. And by the way, that means those numbers are suspect, right? I mean, they could be accurate to 3 significant figures, maybe 5, right? Maybe 1, right? Or in economics, the sign is suspect, right? Or something like that. I mean, you just don't, so there's places where it's dominated, right? I mean, so, there's extremes here, right? All right. So the point is, though, that in all these cases, there is error in the data. I mean, that's just period, right? And there are ways to handle it simply. Simple methods. We've seen one already. Regularization is essentially a method to choose x's that are not extremely vulnerable to changes in A. For example, that's a very simple example of a robust optimization problem. But there are plenty of others, right? By the way, how is parameter variation handled in real life? So what do you think is by far the most prevalent method for handling the fact that your parameters are not known? In real life, I'm talking about when people actually solve things. What? Ignore it. Thank you. That is absolutely correct. That is by far the prevalent method. Now, that's okay, in my opinion, provided you do one thing, which then makes this okay. What would that one thing be to do? It's the least you could do. So you've just solved a problem. You assumed that all your data was accurate. They're double precision numbers. You got them from, Bob or whatever, or some other intern. Doesn't matter. You got the model and you did it. What should you do now? generate a new A with the entries changed by a plausible amount. Everybody got this? Right? And you just simply test the X you found before with the new A. And if things are way off now, then you know that you cannot ignore safely robustness. Everybody got this? I mean, this is incredibly simple, but it's unbelievably important. It's actually shocking to me how many people don't do this, right? So, but this is just completely standard. If you come up and say, oh, wow, I've got a fantastic force sequence to land an airplane. You got to see this. It's unbelievable. Yeah, it's like, no, people don't even notice it when they're, yeah, and you say, okay, fine, here it is. You absolutely have to go back and change the model, change the total mass, move the center of gravity, and resimulate the same thing with these changed parameters. And you have to do 10, 100 of these. After which, by the way, you know absolutely nothing, I might add, technically. But, I mean, from a strict point of view, right? But at least you've done the common sense check. Everybody got this, right? If you come and say, oh, I've got a trading strategy, it's unbelievable. And they go, really? And you go, oh my God, you should see what it did last year. Unbelievable. And then you'd say, well, did you try it on the year before? Yeah, no. The main method, traditional method used for handling uncertainty in data is to ignore it. And I would say that's actually a perfectly respectable option, provided you do a posterior analysis of the effect of the variations. Then it's totally legit. I mean, assuming the posterior analysis reveals that it's okay, it works fine. Okay. Now, the next step is to have a heuristic that kind of is a heuristic for kind of making sure things don't get too wacky when the parameters change. That'd be like regularization. Absolutely fine. Again, you do a posterior analysis to understand if it works. And the new thing, this has been coming up maybe in the last, could be 20 years, but then it was done by a handful of esoteric, work by academics. It's now coming on mainstream. It's this. You simply take into account the uncertainty directly in the problem statement. Okay? And so these are called, that's robust optimization, and this is a special case. Okay, now we're jumping back to the specific. That was the background. We're jumping back to the specific problem we're looking at. So you have to have a model for how A varies, right? And in one, it's stochastic. You would say A is random, and you'd describe its distribution. And the distribution could even be finite. Like you just say it's got 25 values with these probabilities, right? By the way, that's an extremely reasonable thing to do, because what you do is if you track the provenance of A and it came from other measurements and data, then what you'd do is you'd go back to someone there. It's like cross-validation or something, if you know what that is. But you'd go back and you'd say, here's a model for my chemical process. And you go, great. How'd you get it? And you go, from data. I fit it from data. And you go, you know what? Fit me a separate model for every day of the week. I'd like you to fit a model for your chemical process for Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, right? So you get 7 models now, right? Now, by the way, if you look at these so now you have A Monday, A Tuesday, A. Now, by the way, if they're all completely different, you should just turn around and go away. Because basically, your host, there's nothing you can do there's nothing intelligent. This is not a place for us to be doing anything, right? Because it basically means there's no consistency and it doesn't make any sense. Okay, fine. So hopefully, all the entries of A Monday, Tuesday, Wednesday, they're close. In a worst case, robust fitting or approximation problem, you would do this. You would say, I'm not going to use a stochastic model. Instead, what I'm going to do is I'm going to have a set of values of A, and I'm going to judge my fit by the worst case, right? And by the way, there's everything in between these two, right? So these are just two, and there's incredible, complete nonsense, silly religious wars between people who, and it makes no sense out of a context, right? And in any particular context, it makes tons of sense to discuss what would be a reasonable robustness model. But outside of a context-free, it makes no sense whatsoever, right? Mostly, what you do. This is sometimes called minimax fitting. That doesn't have a name. Yeah, it does. It's called stochastic optimization. But okay, so that's the idea. Now, solving these problems is tractable only in special cases. I mean, in a lot of cases, it's not tractable at all. But some are. Here's a super duper simple example. We have a matrix which has a 1 parameter variation. It has the form A0 plus U, A1, and U varies, between, let's say, 1 and -1. something like that, right? So basically in matrix space, you have a little line segment, right? And, hopefully it's not a giant one, right? But it's a little line segment. And of course, in a more realistic one, it's varying in a ball, or I don't know. But this has a line segment. That's it, right? So, okay. And you can actually easily imagine where the dominant variation is one line, right? Because it could be some process that you run. And in fact, to first order, it's mostly affected by, say, ambient temperature. And so the ambient temperature goes from, 10C to 35. And that changes the model, right? I mean, things like this happen all the time. All right. So what you do here is, in this case, you can solve all these problems, all of them. And so this shows you a couple of the solutions. So x nom simply ignores it entirely, minimizes this. And then what you do is you take this x, and I calculate the norm here as a function of u, and that's plotted here. So this is x nom. And the nominal point is right here. And look at that. Of course, by definition, it has to get the lowest value. This is the nominal value. Sure enough, it does. Gets the lowest value. It's right there. But then you see as u changes, you start paying for it, right? By rising cost. Okay? So here's the x stochastic. That minimizes the average over the interval -1, 1. So over here to here, that gives you this one here. Sorry, this one here. This one here. This is x stochastic, right? And you can see that you pay for it in nominal performance, right? Because the stochastic one dips not as well. So the nominal performance is a little bit worse. But now as u varies out to be 0.7 minus 0.8, you're actually doing much better. Okay? So everybody, I mean, this is kind of clear, but that's the idea. And the final one shows worst case. And that's this last one. It's very flat. You've paid for the cost in nominal cost. You do much worse than if it's nominal. But if you look at the minimax over -1, 1, you do very well, right? So this is just to illustrate. Very simple thing. Okay. So we can also handle, I mean, as an example of another thing that has an analytical solution would be stochastic robust least squares. So let's work that out. This is absolutely traditional, and it's kind of cool, actually. And it relates to something we were talking about earlier. It's this. Suppose your matrix A has the form A bar, a nominal one, plus U, where U is random, zero mean, and has expected value U transpose U as P. Okay? So we want to minimize the expected value of the square of the two norm of this thing. And of course, the expectation is over the distribution of U here, right? So you just work that out. I mean, you expand this thing. The cross terms, like here, there's two, when you expand this quadratic, there's a cross term which is x transpose U transpose A bar x minus B. You take the expected value over U has zero mean. Those go away. So the cross terms drop out in the expectation here, right? Leaving you with the nominal cost plus this thing, and you get that. And it's super cool. You recognize that immediately. That's regularization. It's quadratic regularization. And in fact, it's even cooler. It basically says, if you do Tikhonov regularization like this, what you can claim to be doing is you're actually minimizing this, which is super cool. And you say you're minimizing this thing where instead of thinking of the matrix A as fixed, you're actually taking into account that every entry varies. They're all independent and have a variance, which is, I don't know, something like delta over n. I mean, you can figure out what it is, right? Everybody got this? So it's actually super cool. So if you do Tikhonov regularization or ridge regression, I guess if you're in statistics, you do ridge regression, you don't have to justify it to anybody. But if you're in a field where they don't have a special name for Tikhonov regularization and they ask, what are you doing? You could say, oh, I'm doing robust least squares. I'm taking into account minor variations in the A's. Everybody got it? Now, we can do some worst case ones. I'm not going to go to the details here because they're kind of hairy. This is quite new. This is something that's like 15, 20 years old. So let's do the case where the matrix A actually lies in an ellipsoid of matrices. Again, completely reasonable. And what we really want to minimize is the worst case. So it's going to be a weird thing. If you like, it's a game or something like that, or it's like a game. Basically, you commit to X first, and then your opponent will then choose the worst possible A. That's what this is, right? So this is so it's something like that. And there, turns out, something like this you can solve exactly, right? So if you work it out, and again, I'm not going to go through any of the details because they're quite hairy, and in some sense, it doesn't really matter. I mean, you should go back over and check it. It turns out that here, when the opponent is calculating what's the worst thing I should do, they've committed to X, and I'm going to find the next. You end up solving this problem, and that is a non-convex problem if I ever saw one, right? Because the objective is you're maximizing a quadratic, right? Convex quadratic, right? Now, you haven't seen this yet. Maybe you did or something, but it's maybe time for you to know this. So I'm going to say it. I'm going to use this as an excuse to let you know. There are some generic non-convex problems that can be solved, okay? And the simplest one has a very simple and short description length. Any optimization problem involving two quadratics can be solved globally. Okay? Everybody got that? That's in an appendix of the book. You should read it or remember what I just said. Okay? Because it actually comes up in a whole bunch of different applications, right? So, and that's convexity, not convexity. And you know, and by the way, you know this already. If I walked up to you and I said, "Oh, you know, please help me solve, you know, this problem. A is symmetric, you know, right? Something like that." I said, "Please maximize this thing." Right? How do you maximize that subject to that? Well, that sure is no convex optimization problem, right? Because this thing was not concave unless A is unless A is negative definite, okay, negative semi-definite, right? There's no way that's never a convex constraint, right? That's a sphere, right? So that's a hideously non-convex problem. But everyone here knows the answer, knows this can be solved. I mean, it's basically an eigenvalue problem, right? The answer is the largest the eigenvector corresponding to, it's the largest eigenvalue and blah, blah, blah. Everybody got that, right? So, all right, this fits the thing I'm saying here. That is an optimization problem, and it involves exactly two quadratic functions. And the general statement is this: any optimization problem with exactly two quadratic functions can be solved exactly. And so what that says is, you know, if someone says, "What are you doing?" "I'm taking a class on convex optimization." "Oh, is it interesting?" "I don't know." And then you say, "Well, are all problems convex?" You go, "Oh, no, no, no." And someone says, "Name a widely used, useful problem that's not convex." The first thing you should mention, I would hope, would be things like singular value decomposition, PCA, eigenvalues. Okay? Well, you know what this says? This says those are convex. Sorry. So, I mean, it's kind of weird and obscure, right? And the reason, by the way, is that the duals of these problems have zero duality gap. So, anyway, all right. So that was just my weird little aside, but this is an advanced thing. This is not a simple thing, but it's an extremely good thing to know, right? So, and if you include these, you'd be very hard pressed to find problems, any problem you can solve that is not convex if you include these. So, that is an open challenge. So okay. So this one actually can be solved by solving its dual, which is this SDP. Doesn't matter. The fact is, zero duality gap, right? So, okay, now it's fine because you want to minimize over choice of x, this thing, but this thing has just been expressed as a minimization function, right? And therefore, you minimize both at the same time. You solve this SDP, and you actually solve exactly this robust least squares problem, right? Here, what this is the following: is we have I mean, this is a very simple thing. We actually have, it's a two-dimensional ellipsoid. I guess you might even call it an ellipse or something like that, of A matrices. You commit to X, and then we'll find like the worst. In fact, what we'll actually plot here is a histogram of the residuals, right? Now here we'll take U uniformly distributed on the unit disk. Okay? And we'll take several values of x. The first is, suppose you just completely ignore uncertainty and you solve the least squares problem, minimize a0 x minus b. That's the nominal problem. You minimize that, and you get this distribution of residuals, right? So they're all over the place. And you know, some of the residuals are 4 and 5. And by the way, how would you describe what happened in this situation over here on the left? Dumb luck. That's exactly what it is, right? You committed to an x, And in fact, there are A's that make the residual smaller than you thought it was going to be. Okay, so that's just dumb luck. But you pay for it over here. Okay, now you turn on Tikhonov regularization. And you can even imagine, I mean, one could even make a cartoon of this, right? You can imagine turning the Tikhonov regularization knob. When it's 0, you get this distribution. Okay? As I turn it up, what happens is that distribution will end up looking like this. This is sort of the best looking one, the Tikhonov regularization one. And you can see it did exactly what it was supposed to do, right? Tikhonov regularization is something like a heuristic it's a heuristic for giving you a robust solution. And you can see, and here robustness, we're going to make it very vague, you get a tighter distribution of residuals, okay? And in fact, the expected value of this distribution is smaller than this one. I mean, I'm not going to work it out because it's too simple here. But you can see it's simply, from a robustness point of view, a better solution. Okay? So this shows you exactly what people have known for, I don't know, 50, 100 years. That you had regularization, and one interpretation of regularization is to make your solution more robust to variation here. Okay. Now, the exact robust least squares, the one that minimizes the worst case residual over this ellipsoid of matrices, is the one you obtain by solving this this SDP here, right? So you solve that SDP there, and you get the following distribution of residuals. It's right here, and this is right there. That's the number, right? That is the optimal. That's the globally optimal number for the best you can do, right? And so this is kind of the idea. And I think these distributions sort of explain everything, right, about what you're trying to do here and what robust optimization does, right? So this is the kind of this is the idea. Notice that when you I mean, we can anthropomorphize this a little bit, but one thing interesting to notice is all of these, everything over here in either the Tikhonov regularized or the nominal solution, all of those are cases where by dumb luck you did better than the robust least squares, right? And what's interesting though is when you typically push the worst case residual down, usually an effect is that actually the best case actually goes the other way, right? And I mean, this is sort of natural, but and again, what I'm saying now is extremely vague. These would not be arguments you would be allowed to make in public, but it's just something to point out.